Hello, and welcome to the following presentation of a case study on an ethylene product pump. This particular case study focuses on some mechanical seal design enhancements that help improve reliability in this particular application. I'm going to be your presenter. My name is Brian Kalfrin. I'm the Senior Regional Engineering Manager for the Americas and John Crane, based out of Pasadena, Texas. I've been with John Crane 22 plus years, focusing on mechanical seal reliability and design improvement for challenging applications like this one. This particular case that we're going to review is focusing on an ethylene product pump. It was for one of the largest ethylene and polyethylene production complexes in the world. This is located in Alberta, Canada. It's an API BB5, um, very arduous conditions for the mechanical seals. Pressures in excess of 1,000 psig at lower sub-zero temperatures, so negative temperatures, which we'll see. And the shaft speeds are in excess of 5,000 RPM. So a very challenging application for a mechanical seal, end-face mechanical seal, to overcome in terms of heat generation and friction and all the variables that are associated with that. This particular seal originally was supported by a Plan 11 and 52. There was some challenges with that as well, which we'll elaborate on. The supplied seal, as it was able to achieve between 18 to 24 months mean time between repair. There were some known failure modes that were identified that a alternative means of sealing were applied to address in both the dynamic secondary seal and abrasion and breakdown. And there was some additional modifications to both the face features to support lubrication and hydrodynamic lift to help promote face separation and minimize face generated heat, along with some additional modifications to the Plan 52 system through some CFD modeling that helped improve circulation and cooling as well. All of these efforts were incorporated into a redesigned seal, and that was installed in September of 2021. And to date, that design has been performing very well. And what we'll go through in the following slides is kind of step-by-step documentation of each aspect, kind of the findings and how it was ultimately implemented into one solution at the end of this process. So to start off reviewing this case study, there's a little bit about the application details and history shown here on this page. The original mechanical seal is classified as a pusher, what we call a pusher balanced mechanical seal. It's a dual unpressurized arrangement supported by an API piping plan 11 and 52. The original seal utilized antimony filled carbon and sintered silicon carbide seal faces, a low temperature FFKM elastomer, and an integrated circulation device, more commonly referred to as a pumping ring, on the containment seal, which helps to facilitate the lubrication of the buffer fluid in the Plan 52 loop. The inner seal in this arrangement receives cooling and lubrication from the process fluid, and that's supplied from the discharge regions of the pump through the API Plan 11 piping. The original mechanical seal had undergone several design adjustments since commissioning, both to kind of the internal geometry of the faces, and this was done in an attempt to optimize the performance in terms of mitigating face generated heat and also controlling leakage. In its current iteration shown here, it was achieving a mean time between repair, or MTBR, of between 18 and 24 months. The equipment owner was happy with this, but they were looking to improve the MTBR of these pumps overall, including the mechanical seal reliability, to meet scheduled outage intervals of at least 60 months. So as mentioned, the application details and history, we were achieving about 18 to 24 months with the original seal. When the seals did fail, these are some of the typical failure symptoms as noted here. On the primary seal faces, we had extreme elevated ID wear and ID chipping. In particular, the dynamic O-ring, which is item 4 shown in this picture, had signs of fretting, damage, and hang up. There was also evidence of polymerization of the process fluid at the seal faces, which is fairly common in ethylene services, especially when face generated heat produces temperatures that are conducive to form polymers in those localized hotspots. And the containment seal overall was in good shape, but still signs of dynamic O-ring hang up and fretting. So that would have been item 13 for the containment seal, consistent again with what we would see in the primary seal wear. In one occasion during pup shutdown after a primary seal failure, the secondary sealing element, item number 4, as I mentioned, suffered a pretty significant hang up event. And so combined with some small rotor axial movement that was determined in vibration trends, which were right around 0.003 of an inch, this translates to a fairly significant variance in the gap between the seal faces. And this has actually resulted in a significant ethylene leak to atmosphere. Overall, the risk of hang up of that secondary sealing element to atmosphere was evident, and in once the primary seal had failed, you could have a continuous leak into that intermediate cavity, you cause auto refrigeration, and it's contribute to that containment seal dynamic O-ring hanging up as well, and that's going to again lead you to a path of least resistance for that ethylene to leak out to the atmosphere. These are some pictures of some of the typical failure modes observed, um, with both the seal faces and also the secondary hardware, adaptive hardware, and the secondary sealing elements. Of note is the primary seal dynamic O-ring in the top left with heavy wear and heat damage. The subsleeve coating, which that primary ring uh, dynamic O-ring rides against, shows very visible fretting and damage, even under magnification. And this was despite the fact that the that subsleeve had a hard coating, an HVO applied tungsten to the surface. Uh, so even with that hard coating, you were still getting fairly significant fretting damage from subtle movements, kind of an oscillating motion of that dynamic O-ring across that surface. Looking a little bit in deeper detail at the seal faces, the mating ring, you see the evidence of the polymerized ethylene on the contact surface on the left, and on the right-hand side, you see the primary rings, ID chipping, heavy wear, and blistering. The heavy wear, the ID chipping, the scoring and blistering, these were all suspected to have occurred right at the seal faces, and again, that's indicative of excessive face-generated heat that's not uncommon in low molecular weight hydrocarbon surfaces such as this one. And now we look at the containment seal, we see some also indicative wear, kind of consistent with what we see on the primary seal, heavy face wear, grain pullout and blistering. Some contaminants, some of these contaminants are carryover from uh, leakage and byproducts past the primary seal faces, and then they kind of uh, played out and replicate the failure mode on the containment seal faces as well. So when we look at the comparisons of the original seal versus what is proposed side by side, we can see some notable differences that we'll discuss briefly. Most of the solutions up until this point to kind of control the seal face gap, or what we would consider a passive solution with emphasis on boundary lubrication and hydrostatic fluid film formation, There were some attempts to introduce hydrodynamic face features like hydropads on the original seal, and that helps to overcome uh, a, a little bit of the side effects of excessive wear that would reduce reliability, especially when you look at high pressure and high velocity applications such as this one. However, with those type of passive face treatments, there is some inefficiency, and those type of designs they can be augmented by looking at more enhanced lubrication inducing features to help not only provide a more stable fluid film at the seal faces, but also help to manage the lubrication and leakage control more effectively. So a more successful solution relies on technology that offers full fluid interface lubrication for improving reliability, but also features that mitigate the leakage, so active leakage reductions. If we looking at the face features, we accomplish this by using a combination of um, an interface pumping arrangement that helps to both supply fluid to the sealing gap, but also a means of returning it to a pressurized fluid space. So we do that with these micro machining techniques that give us a more refined sealing interface pattern to help marry those two effective uh, practices: good face lubrication, low leakage to the atmosphere. In addition, we'll look at the secondary sealing element. The pusher seal, as we see on the left, uh, it's called a pusher seal because the secondary sealing element is going to move in the axial direction as the seal faces wear. In normal operation, that O-ring is pushed forward by the spring load and hydraulic forces. In operating scenarios where the pump might experience repetitive axial movements with the shaft moving from non-drive end to drive end and so forth, the O-ring is going to move across that metal sleeve surface. In addition, instability at the seal faces due to vaporization of the process and expansion of the process fluid as it changes state can exacerbate this issue, and you'll have continual wearing action on the O-ring, which ultimately degrades and results in a seal failure. So any pusher type secondary sealing element, a wedge, a spring energized polymer seal, and certainly an O-ring is going to be susceptible to this. So one of the proposed changes, in addition to the improved face features, is to use a non-pusher secondary sealing element, which is what we see uh, in that L-shaped feature on the right-hand side that seals static to the shaft, and then that forward flange portion articulates axially, so you eliminate that repetitive degrading movement of the O-ring over time to that wears due to that constant shuttling back and forth. So to model some of the improvements here, some FEA analysis was completed, and this is a summary of what we see with those looking at a side by side of FEA results between the original mechanical seal, inner seal, and then the proposed design with the face design features. So overall, with the lower hydraulic balance of the redesign, you get improved film stiffness, increased face separation, and lower overall face generated heat. The net reduction in the heat generated is directly attributed to the lower hydraulic balance with the proposed design, and with the active face features that you see in the bottom right corner, uh, they provide the improved leakage control, and therefore you mitigate the need for any type of increased face loading that you typically require with the passive control of saying having hydro pads on the surface. So because we're able to provide that stability uh, with the seal interface itself, we're able to gain some benefits by reducing the heat generation uh, and overall average interface temperature. So taking this seal away from a condition where it's likely to possibly form polymers and lead to the other, uh, lead us away from the failure modes that we had typically seen in the past. For completeness, in addition to looking at the seal faces and the secondary elements, we wanted to take an overall look at the effectiveness of the flush flow, and particularly the flush flow for the inner seal, the API Plan 11. And so we considered the recommended improvements already, and then we just wanted to validate the effectiveness of that primary seal flush. So the inner seal is lubricated by the process fluid supplied by Plan 11. So you're taking circulation from discharge regions of the pump and providing it to the seal chamber and to the seal face area. So to do an effective analysis, it was important to evaluate both the existing and the proposed seal performance in terms of how effective is the Plan 11 in helping to remove the seal generated heat. Uh, Taking a look at the piping and the integral flow diverter, which is shown above the seal faces with those radial holes there. And this was done using a computational fluid dynamic software analysis. And this study is effective because it's able to model the flush flow distribution through the flow guide and the interconnecting piping uh, very quickly with the aid of the software. So for the CFD analysis, these were the inputs and the boundary conditions specified. We had the fluid properties of ethylene at the operating temperature, the specific gravity, the viscosity, the specific heat. The Plant 11 flush was sourced from first stage discharge pressure, so uh, we assume that to be 1223 psig, which is about 1/12 of the pump differential. The seal chamber outlet is equivalent to the suction pressure, so that would be the pressure downstream of the throat bushing. This is a little above 1100 psig, and so the differential pressure from inlet to outlet is about 121 psi. The seal chamber throat bushing had a 10 thousandths radial clearance over the shaft, and then we know our shaft speed 6,200 RPM. For the software, you apply, you get an estimate on your face generated heat, and you apply that input to the nose of the primary ring as a uniform heat flux, and that tells the CFD software where kind of an input of heat is continuously, and then you can gain some understanding of temperatures around the periphery of that surface, and certainly around a key area of interest, which would be your interface, your sealing interface. And by doing that, you can get an understanding of if there's going to be any hot spots or any areas of uneven cooling around the periphery of that surface. So all the dimensional details and operating conditions were confirmed with the end user, both through measurement and also pump maintenance record documentation. When we look at the assumptions for the CFD analysis, the CFD software is going to solve for one of three outputs depending on two inputs. So in this case, we provided the throat bushing details and the differential pressure through the system, and then the software would solve for a flow rate required to satisfy those criteria. So what we're looking at here to try to evaluate is not only that the cooling flow is achieved, but how efficient is this flow guide in diverting the cooling flow to where it's most required, which is at the seal faces. So there's several iterations to the analysis that were done. These were some of the kind of relevant screenshots that show temperature and velocity um, through the arrangement. Now this is with the original existing inner seal arrangement. So once the analysis was completed, and the model geometry was generated. Uh, Fluid properties, they're maintained from the analysis, and the boundary conditions kept consistent. The proposed uh, design had a relatively high heat generation of about 23,000 BTUs per hour, and then we're taking that into account and looking at these outputs. So after a few of these simulations, the existing flush porting model results, they show generally good performance. Um, Overall, your heat reduction is generally consistent and equally distributed through the flow guide. If you section the model geometry through one of the diverter holes, it's noticeable how the fluid flow tends to kind of hug the radial wall of that seal mating ring, and basically the fluid comes in, kind of hugs that radial wall and gets shot out and impacts the internal bore diameter of the flow diverter prior to exiting the seal chamber. So you can kind of see this phenomenon repeat through every hole around the periphery of that seal face, and that's further amplified when you look at the velocity end view at the top right, um, how those velocity regions kind of repeat around the periphery of the surface. So when we look at the proposed CFD output for the proposed design, one thing that we noted is that the proposed design had a lower face generated heat. It was around 18,000 BTUs per hour, so a lower value than the original due to the reduction in hydraulic balance primarily. And then we also looked at, how this overall design would fare with the same style of flow guide. So one thing to note is that the OD of the mating ring with this configuration is different. There is notches and anti-rotation pins on the OD of the mating ring, and in order to kind of resolve those in the model, um, they had to be kind of resolved into a simple slot for the geometry and for the software to work. And we do see some net benefits of simulating how those notches actually come into play when we look at the injection of the flush flow into the interface area. With as with the previous analysis, the model outputs yielded some good results in terms of equal flush flow distribution through these holes. When we section the geometry through one of the diverter holes, especially at the mating ring pin slot location, that area is of particular interest because we see now that the slots on the OD of that mating ring aid in kind of channeling that fluid away more efficiently out of the seal chamber area, and that's in the image on the bottom right, where you see that high velocity flow of fluid as it gets kind of pulled through that slot on the OD of the mating ring and more effectively channeled out, as opposed to being kind of directed up into the bore of the flow guide. So and interestingly enough, the calculated flow rate with uh, the proposed design versus the original was higher. It was 18 gallons a minute versus 16 GPM. So the combined effects of the optimized face geometry and the effectiveness of this particular arrangement with the porting and the configuration of the mating ring actually helped us get uh, more effective flush flow through this inner seal piping system. So once the concerns associated with the performance and the inner seal were kind of satisfied and put aside, the overall performance of the containment seal was evaluated. Now, it's important to note that the current containment seal was considered to have very good performance overall. So at minimum, The intent was to try to maintain that level of performance. Uh, Certainly did not want to have any detriment implemented by going to a brand new inner seal design and then making compromises on the containment seal. So at minimum, try to maintain consistency, if not improve on the containment side. There were several design modifications implemented to the containment seal over the years in terms of face geometry adjustments and pumping ring modifications that were implemented and did improve performance. So they had a very reliable design to start with, but the recent failure observations did note that the dynamic O-ring in the containment seal was suffering from the same degradation and wear as the inner seal dynamic O-ring. So it was important to consider utilization of a non-pusher secondary sealing element in the containment seal as well, uh, if one was going to be considered for the inner seal. So to assist in the analysis, some additional FEA modeling was again completed and utilized here. Several iterations were considered to first compare the performance of the original containment seal, a proposed containment seal with a non-pusher element and identical face geometry, and finally a version utilizing improved seal face materials. So what you see here are some of the outputs of those efforts, and to compare several variables, including heat generation, average face temperature, PV, min film thickness, contact pressure, and leakage. So option one considered only seal face geometry modifications, basically identical to the original containment seal, and then just using a non-pusher secondary sealing element. And those outputs were very desirable. Um, of note, those at the average face temperature was a little high, but manageable compared to the performance of the existing containment seal. So certainly comparable and on par. Option two considered identical face geometry as option one, but with the inclusion of uh, enhanced seal face material pairs. So the enhancements to the material pairs was to incorporate a silicon carbide graphite composite face running against a diamond treated silicon mating ring. So utilizing the diamond treatment to hard face materials is advantageous as especially in high duty applications, as it's going to yield a much lower interface temperature, and that's directly attributed to the very low coefficient of friction of diamond. Additionally, the inherent topography of hard faces allows for more fluid in the interface, so that's advantageous in this instance because we have a very high speed and a very low differential pressure. So by taking advantage of these inherent material surface features, we ensure we get a stable fluid film and we maintain low asperity contact. So option two was selected for the improvements in interface temperature reduction and the reduced PV values overall. When you look at that versus the original, the most significant change was uh, still having manageable leakage, but then having a very significant reduction in average face temperature. So you can see the drop from 305 to 310 degrees F down to about 260 degrees F. So moving that interface temperature away from higher temperatures where you could potentially start to degrade the buffer fluid, especially at high temperature and and higher shaft speeds. So the final component or assessment in this case study that we'll discuss is the support system piping and analysis of the API Plan 52. So uh, the Plan 52 specifics are shown here. These are the components of the system and the buffer fluid that was in use. Um, it was beneficial to consider reviewing the Plan 52 support system piping, look at the effectiveness of the internal circulation device within the mechanical seal, and evaluate the performance of the pumping ring, the circulation device. How's that interplay with the interconnecting piping, and overall the support system details, and just to make sure that we had a robust uh, and efficient Plan 52 circuit that was giving us the cooling and circulation that we were looking for with the implementation of these other design features, both on the proposed uh, inner seal and containment seal. So there were several pumping ring iterations that were considered, and they're shown here. So the original design is shown in the top left, and then there were several revisions. So they're labeled R1 through R5. And so they're shown here through various stages of concept in CAD design, going from milled slots to through slots with radial holes to through slots with radial slots on the back side of it, and then also some additional modifications to the seal sleeve. To summarize these results, the original pumping ring design yielded a circulation rate considering the system resistance of about 9.3 gallons per minute. So how we got the flow rate was to map the system resistance curve based on the interconnecting piping size, length, number of tubing, bends, and restrictions, and to get an output of circulation through of the pumping ring performance through the CFD model, and then kind of overlay uh, the head and capacity curve of the pumping ring with the system resistance curve, and to get our flow rate. So the original design, again, very good performance at 9.3 gallons per minute. The R1 iteration considered adding the milled slots. Um, the flow rate was actually significantly lower than the original design. And so the thought behind the milled slots was to try to mimic the slots of the mating ring on the inner seal that seemed to provide some benefit there, but did not provide any kind of replicating that with the pumping ring, and the containment seal didn't really provide any additional benefit. So that was discounted. R2 improved on that slightly with the additional through slots on the mating ring to get up to 10.5 gallons per minute in circulation rate. But there is room for improvement that we'll see in the CFD outputs in terms of how much that fluid kind of penetrates and circulates around in the buffer cavity. And that's really what we tried to look at with the CFD model, was both maintaining consistent circulation, but then also how efficient and how effective the circulation of the buffer fluid is in that circuit. The R3 iteration had comparable circulation rates to the original, and the addition of the radial holes um, through the section of that pumping ring geometry actually helps to improve circulation in the adjacent regions of the containment cavity. So taking that a step further with R4, you can see the circulation rate remains consistent, and then the CFD prediction actually shows additional fluid circulation further into the containment cavity, now getting actually more penetration beneath the inner seal face area. And so the final kind of result of doing this analysis was to look at R5, which kept the pumping ring geometry the same, but then added these milled slots or radial slots into the OD of the seal sleeve, and that gets the best overall improvement in terms of maintaining circulation rate, but also having more effective turbulence and distribution and circulation of the buffer fluid in the cavity. So the CFD outputs give you a better indication and picture of that, going from R2 at the top left corner to R3 at the top right to R4, and then finally to R5. So you can see kind of the maturation of the process as R2. You can see the turbulence and the velocity, and then those regions of dark blue that are kind of stagnant. And as you go to R3, you can see the velocity kind of further penetrate back towards the left. Towards the left is our region of area beneath the inner seal faces, center field faces, which is normally a dead spot or dead zone. And now you can see with finally, when you get to the R5 image, that velocity is further penetrating all the way throughout the buffer cavity, and giving us an area where we don't have really any stagnant regions at all, especially beneath the inner seal faces. So by improving that velocity through the fluid in all those regions, we're actually helping to further kind of dissipate heat and help remove any kind of residual heat away uh, from the inner seal, which is critical in volatile fluids such as this one. So overall, this is the finished design as we see it. So you'll note the non-pusher secondary sealing elements on both the inner seal and containment seal, the porting on the flow guide for the Plan 11 flush, and then you can see our pumping ring, and then kind of ghosted images of our slots on the sleeve beneath the inner seal as well, which were the modifications implemented as part of the overall analysis of every single facet of this design. So inner seal, containment seal, Plan 11 piping, and then Plan 52 support piping. So how this is designed is how it was presented and installed, and then the summary of the results. That proposed mechanical seal was installed in September of 2021. To date, based on trends and discussions with the end user, they've seen a 10 to 20 degree C in Plan C temperature reduction in Plan 52 oil temperatures observed on both the drive end and non-drive end. So very consistent reduction in Plan 52 temperature, which tells us that the circulation rate of the pumping ring and effectiveness of those design features is very good and matches the anticipated calculated outputs. The inner seal leakage results, they're measured by reservoir pressure transmitter measurements. There's been no change in performance from over the life of the seal, even though it's gone through several stops and starts since installation. The leakage rate is slightly higher than the original, but that is anticipated based on the fact that we are actually lowering the hydraulic balance and increasing the fluid film at the inner seal faces. So while we're seeing actually a slight increase, it's manageable, and in fact the leakage rate as predicted has decreased over time, and that's just a function of the seal face profile wearing in and adjusting and compensating once it relaxes to kind of a steady state, more continuous operation, and that's consistent with the FEA results as well. The end user, they plan to actually proactively pull this seal for inspection in the fall of 2023. That's their tentative plan. They may divert from that, but they were interested in doing kind of a proactive inspection just to kind of validate the wear, if any, and kind of confirm that the modifications were resulting in the desired outcome. Again, overall, this design has provided expected performance, and there hasn't been any detrimental impacts even during operational outputs. So the performance of this seal design has further substantiated what we know about utilizing advanced analysis tools, and then coupling that with very good and documented application expertise. That's a good recipe for success when you're trying to address problematic applications such as this. The design features that were highlighted in this case, the active face features, the non-pusher secondary element, and certainly some of the features around the circulation device and the analysis tools, they're worthy of consideration to improve and extend reliability of mechanical seals, especially in low molecular weight hydrocarbon surfaces such as this one, which are always very challenging to seal. So I thank you for your time and listening to the presentation, and certainly invite questions if you have any to leave them in the chat, or feel free to reach out to me as well afterwards.